Okay, welcome everybody to the Quantum Nanoscience session of Quantum Days. I hope everybody had a chance to enjoy the keynote talks just before. This session is focused on talks with three speakers. Yuwen Chu, who's an assistant professor at ETH in Switzerland. Joe Salfi, who's an assistant professor at the University of British Columbia. And Na-Young Kim, who's an associate professor at Waterloo. And their research covers different aspects of building or studying nanoscale systems for quantum technology. So with that, it's my pleasure to welcome Yuwen to present the research.
Great. Thank you so much, Paul, for the introduction. Let me just share my slides very quickly here. Let's see here. Okay, do you see my slides? Okay. Yes. All right.
Looks good. Okay,
wonderful. All right, so yeah, I will be telling you a bit about some of our latest work on the field of circuit quantum acoustodynamics. And in a few words, what that means is essentially using the tools of superconducting microwave circuits to control and measure the quantum states of macroscopic mechanical resonators. Okay, right, so in a little bit more detail, the idea of circuit quantum acoustodynamics, or circuit QAD, is the following. So as many of you might be aware, there is a very well-developed field of circuit quantum electrodynamics, or circuit QED, where people are building all kinds of very sophisticated tools for controlling quantum circuits made out of superconductors, and using this to build various technologies such as quantum computers. And the idea of circuit QAD is to adapt some of these tools and use them to explore the quantum behavior of mechanical motion. And here I've just drawn a cartoon of a couple of these different types of mechanical objects that can be incorporated into these systems. So they range from phononic crystals, which are periodic structures that can confine sound, just as a photonic crystal confines light, to, for example, acoustic waves, sound waves, essentially propagating inside a crystal. And the idea is to combine these things together to, on the one hand, again, use these sophisticated quantum tools from circuit QED to control these mechanical systems, but also to think about whether these mechanical systems can contribute something to these quantum circuits, right? I mean, mechanical motion is a very different degree of freedom than electromagnetic circuits, and maybe have some unique properties that could be useful when they are incorporated into quantum technologies. And I'll get back to that at the end of my talk. But for the most part, we'll be discussing essentially what are the sort of latest ways that people have come up with to control the quantum states and to measure the quantum states of these mechanical objects. Okay, so one approach to do this that I'll go into a bit more detail, because that's the one that we'll be using in the rest of this talk, is by using piezoelectricity. And the idea is the following. Let's say you have some sort of microwave circuit. In this case, I've drawn a circuit that represents something called a superconducting qubit. And you can think of it just as a LC resonator, where the inductor, the L, has been replaced by a Josephson junction, which is a nonlinear inductor. And what this results in is essentially a circuit that is also an anharmonic oscillator, unlike a LC resonator, which is a harmonic oscillator. Okay, and that's going to come in be important a little bit later on. But just like in a regular LC resonator, this qubit has a capacitor, which has an electric field. And what we can do is we can put our mechanical resonator together with a piezoelectric material in this electric field. And as you might know, piezoelectricity is the effect that couples electric fields to strain or displacement inside a mechanical object. And a little bit more quantitatively, the idea is the following, right? You have some sort of interaction Hamiltonian that depends on the piezoelectric tensor and the electric field and the strain of these two different objects. And of course, you can then rewrite this in a sort of quantum formulation in terms of A and B, which are the creation, the annihilation operators, for the mechanical mode, which annihilates a phonon, and the qubit, which here we're just representing as an electromagnetic mode. All right. And what are some of the basic things that this allows you to do? Let's first look at what such devices might look like when you combine these mechanical resonators with these electrical circuits. So as I told you before, they can, you can incorporate various geometries. So starting from the smallest, these phononic crystals, and going to, for example, drum heads or membranes, or surface acoustic waves to the system that we use, which are bulk acoustic wave resonators. And you can see that they sort of span a wide range of sizes and geometries. All right, so to go into a bit more detail about what you are seeing here in this very colorful picture here, I'll show you a better drawing of a cartoon of our device. And the idea is basically what I was telling you before in the cartoon picture or in the schematic. What we have here in gray is a superconducting qubit. You see here, this X is a Josephson junction, and these two gray areas here are the two electrodes of your capacitor, which in one case sticks out all the way here into this sort of circular antenna. And the electric field sort of goes from one side to the other. And as it does that, it goes through this aluminum nitride, which is a piezoelectric material, and that transduces acoustic waves into the bulk of this sapphire substrate. And that is our mechanical object, which is also called a high overtone bulk acoustic wave resonator, or H-bar. And this colorful picture you saw is a view from the bottom up, where you see the white here is this antenna from the qubit. And then here in the inner circle is the aluminum nitride. And on the outside is a bit of sapphire. The reason why you see these circles is, as we've drawn here, we have made one of the surfaces of the substrate curved. And that, just like in an optical Fabry-Perot resonator, allows us to confine stable modes of acoustic waves. So you can think of this as a plano-convex Fabry-Perot resonator for sound. Okay. All right, so that's the basic idea of our device. And now what we can do with it is, for example, the following, right? So here I've drawn our the energy levels of our two systems. One is, for our purposes, is a qubit, because it's an anharmonic resonator, and therefore the energy levels are not actually evenly spaced, as you'll see in a second. And we can choose just two levels to use as our qubits. On the other hand, our mechanical resonator is just a harmonic oscillator, and so it has all these equally spaced energy levels. Okay, and as I've rewritten here on the top, they are coupled by this sort of Hamiltonian. All right, and now what we can do is, for example, come in with an electromagnetic pulse, a pulse of microwaves, excite our qubit, tune it onto resonance with our mechanical resonator, so that now the two can exchange energy back and forth. Right? And that's exactly what this Hamiltonian tells you it can do. For example, you can annihilate an excitation in the qubit and create one in the phonon, and so on and so forth. Until eventually, of course, there are other dissipation channels in the system, and so everything relaxes back to the ground state. And indeed, this is what we see in the lab. So these are vacuum Rabi oscillations. As you can see, that when the two systems are in resonance, they do indeed undergo this energy exchange. And the important ingredients for this are, of course, that we start out in the quantum ground state of both systems, which we easily do because our qubit and our mechanical resonators are both in the gigahertz, and we cool them down in a dilution refrigerator to millikelvin temperatures. And the other requirement, of course, is that the strength of this coupling is much faster than the decoherence rates of both systems. All right. Okay, so now we don't have to stop there, right? What I've shown you is how, if we let the qubit, if we excite the qubit and we let it swap over to the phonons, that creates a state where there's one phonon in our system, but we can continue this process where we excite the qubit, let the energy swap over, excite the qubit again, let the energy swap over, and that would be a state of 2 phonons in our mechanical resonator, and we can continue so on and so forth and climb up this ladder of number states in our mechanical resonator. Okay, so now you can sort of imagine that this is the process in which we can make some interesting states in our mechanical resonator, right? So for example, these number states, which are distinctly non-classical quantum states of our mechanical resonator. Okay, so now you might ask, well, how can we measure these states? How can we tell what state the mechanical resonator ended up in? Well, to do that, we're going to work in a slightly different regime, and this is a very, let's say, well-known technique from cavity and circuit QED. And again, this is the idea that we're going to borrow some of these tools for quantum measurement and control from these other fields, which are very analogous. And this is, in this case, called the dispersive regime. So instead of having the 2 systems be on resonance such that they can exchange energy, we can instead make the detuning between these 2 systems, right? So the frequency difference between them much larger than the coupling strength. And in that case, they cannot directly exchange energy, but instead you can rewrite this Hamiltonian as an effective Hamiltonian, which is called the dispersive Hamiltonian, where the effect is basically the following, right? So if you look at this, the form of this Hamiltonian, what it tells you is right here, for example, you have the term A dagger A, which is essentially telling you what is the energy or the frequency of your qubit. And you see that that's going to depend on how many excitations, represented by this B dagger B operator here, are in your mechanical resonator, right? And the prefactor here is called the dispersive shift, chi, which in our particular regime is approximately given by the coupling strength squared divided by the detuning. Okay, and what this says is essentially the following: that every time you have an additional phonon in your system, the frequency of your qubit will shift by an amount chi. And if you're in what's called a strong dispersive regime, where the shift is now much larger than the dissipation rates in the 2 systems, then what you'll see is something like the following, right? That when there's 0 phonons in your mechanical resonator, you'll see if you do spectroscopy on a qubit, you'll see a peak at your qubit frequency, and then if you put 1 phonon there, it's going to shift over by chi. And if you put another phonon there, it's going to shift again by chi, and so on and so forth. And what this allows you to do is essentially, by measuring just the frequency of the qubit, right, which importantly does not require you to exchange energy with the mechanical resonator, you can measure the state of the mechanical resonator, essentially without, in principle, affecting it, right? So this allows you to, in principle, do a quantum non-demolition measurement of your mechanical resonator. Okay, and that's what we are going to, the technique that we're going to try and demonstrate in our circuit QAD system now. All right, so to start, what we're going to do is, well, let's start with something simple. So we're going to put our mechanical resonator into a classical state. So we're going to drive it with just, again, a coherent microwave pulse, and that puts it into a coherent state, right, which I'm representing by these variously sized circles here. Excuse me. And then we're going to measure the spectrum of our qubits. And as we said before, we should see are essentially a bunch of peaks at different frequencies, and the heights of those peaks should correspond to the population in each of these number states. And indeed, that is what we see here. So this is the data that we measure. So if you look at the bottom curves on the left here is sort of the amplitude with which we drive our mechanical mode. And you see that if we don't drive it at all, we see a peak here. And as we drive it stronger and stronger, additional peaks start to show up, in this case and the spacing between these peaks is exactly this dispersive shift that I showed you before, right? So this shows that our dispersive shift is larger than for example, the line width of our qubit, and we are able to spectroscopically resolve the distribution of phonon numbers inside a mechanical resonator. All right, we don't have to stop there. This is a classical state of mechanics. We can go through, so I also wanted to mention that, of course, from this, you can extract the distribution of populations, and we see that actually this fits very well to a Poisson distribution, which is what you would expect for a coherent state. Okay, we can then also do this process of creating states of n phonons, exactly, ideally in the mechanical resonator. And again, we can make this sort of measurement. And what you see here is the following. You see that we have essentially these, again, peaks now, but however, the largest peaks correspond to essentially the number state that you try to create in your mechanical resonator, right? So when we say we're going to try and make the state of 2 phonons, we see that there's a most prominent peak at where you would expect the qubit to be for when there's 2 phonons in a mechanical resonator. Of course, we see some additional features to lower phonon numbers, and that is, of course, because we have decay and decoherence during our measurement process. So the mechanical resonator can lose a few excitations in the process. All right, so this is measuring essentially the qubit frequency in spectroscopy, but as you might know, if you can do this measurement in the frequency domain, you can also do it in the time domain by using, for example, a Ramsey spectroscopy sequence, and that is exactly, again, what we do. And the colors here correspond to the same situations as in the frequency domain measurements. And as you can see, right, if we set 0 detuning to be the original frequency of the qubit, you see that when there's 0 phonons, there's just a decay. And as you increase the number of phonons and therefore the detuning of the qubit, you get faster and faster oscillations. And now there's a very interesting point here, which is given by this dashed red line, where you see that if you look carefully, that the lines for the 0 and 2 states are sort of at a maximum, and then for the 1 and 3 states, you are at a minimum here. And this hints at what this time tells you. In fact, if you only measure do this Ramsey spectroscopy measurement for this particular delay time, what you measure is the parity of your mechanical resonator. So it tells you the population in the even number of Fock states minus the population in the odd number of Fock states. Okay. And so that is a very particular quantity. You might ask, why should I care about this quantity, right? And again, just to be clear here, right? Here, because of the imperfections in our system, you don't see that it exactly measures the parity. In the ideal case, right, for the state 0 and 2, it should be 1, and then for the state 1 and 3, it should be 0, for example. That should be the parity. But again, because of decay and decoherence, we don't quite measure exactly that. Nevertheless, it gives us some information. Right. And now if you can measure the parity, you can do something very useful with it, which is to use it to measure the Wigner quasi-probability distribution of your quantum state. And very quickly, what that means is just the following. If you look at the phase space of your harmonic oscillator, right? So here's the real and imaginary parts of some complex amplitude alpha, or you can think of it as the position and momentum axes of your phase space. What you can do is, what we've done is we make a state, and then we can measure the parity, right? In this case, if we take the state of 1 phonon, right, you measure the parity and it should be negative. So I've plotted a blue dot here in the middle of phase space. And what you can do instead is you can do a displacement in between these 2 operations. And that actually is an operational definition of what's called the Wigner function of the state. And so you take each measurement, you take the result, and you plot it with the corresponding complex amplitude that you did this displacement by. Right? And by doing that, you get a bunch of dots in phase space. And if you do it enough times, what you get is essentially pattern in phase space. It's like a fingerprint of your mechanical resonator. And this is what it looks like ideally for the state of 1 excitation. And here is what we measure in the lab. So as you can see, the contrast is a bit lower, again, due to the imperfections in our system. But you see the important features, and in particular, you see that in the middle of this picture here, it's blue, which means it's negative. And it turns out that for a Wigner function, only non-classical states can have negative values. And we can do this for other states that we've tried to generate, different Fock states or superposition states. And you can see here it agrees quite well with some simulations that we did, including all of the imperfections in our system. So the expert and the audience might notice that these Wigner functions look kind of weird, but this is because we have included, for example, the fact that we're not perfectly far in the dispersive regime, and that causes some weird artifacts in our measurements. All right. Nevertheless, we've sort of shown that we can use this method to characterize our quantum states. And to finish up, maybe you might be asking yourself why we want to do this. What's the use of trying to make these states and measure them in a mechanical resonator, right? As I said, we're sort of borrowing tools from these other fields, which are very well developed, like circuit QED. Well, it turns out that if you think about what I'm showing here, is that because of the speed of sound is much less than the speed of light, right? It turns out that the wavelength of sound is much smaller than the speed of light at the same frequencies. And what that actually means is that phonons can, in principle, store essentially more information in a smaller volume than photons. People have also shown extremely long lifetimes in mechanical resonators. Here, for example, is an example where you have seconds long lifetimes, which are much longer than people have measured in electromagnetic circuits in the quantum regime. And the other reason is just that mechanical resonators couple to everything. And so they are being explored as an interesting route to, for example, transducing quantum information between different frequency domains. All right, so I will finish there. And here's just some pictures from our group at ETH Zurich. And also I'm listing here some of our great collaborators that are working with us.
Okay, thank you very much, Yuan. So we have about 5 minutes for questions from the audience. You can either ask them on the Quantum Days app. I'm not sure if anybody's, I don't see any on there yet. Maybe while you're thinking about that, I can start. So with your resonator, are you limited at all by the properties of that, I guess, Plano convex mechanical resonator, or is that pretty well optimized? Where do you see that going?
Right. So we are, I mean, one of the things we're really active trying to figure out is what exactly limits the phonon lifetime. So I should mention, actually, I guess this wasn't really clear from what I've shown, is that the lifetime of the phonons are actually much longer than those of the qubits. So they can be on the order of 80, 100 microseconds or so. And the question, of course, is now what is that limited by? And we have some indications that it might actually still be coming from the imperfect geometry of this Plano convex resonator, as you pointed out, right? We try to design the system to make sure that it is a stable cavity, but of course it is, has a finite size, and at those very high Q, in this very high Q regime, right? If you have any imperfections in the shape, or due to this finite size effects, or if you have any imperfections on the surface, for example, this will of course limit the Qs of these mechanical resonators. And I should mention that in other similar systems, also bulk acoustic wave resonators, people have measured quality factors that are, say, an order of magnitude or more higher. But they're made from different materials and are slightly larger. So we're trying to understand what's limiting us at this point.
Okay. Yeah, so I still don't see any questions in the Q&A on the Quantum Days. I call it the app, but it's all, you can access it from the website, just for the audience to remind you. I'll ask one more, which is, you mentioned at the very end here that these resonators can couple to anything. And of course, this is like the dream of many people working in the general field of quantum mechanics.
Right.
Have you thought at all about whether you could integrate your system with optical systems?
Absolutely. Yeah, that is actually the other, let's say, sort of half of our group is working on exactly that, is using bulk acoustic waves to interface with infrared light, and it turns out that they do couple to infrared light and through, for example, boron scattering. And so our collaborators, Peter Rakich at Yale, for example, has worked a lot on this, and I also worked with him when I was there. And yeah, so now in my group we are looking into sort of combining these two halves together. And of course, even though it is, you can do optomechanics with these kinds of resonators, adding then the circuit part of it is yet another very big challenge. And so there's a lot of pieces that needs to come together there. Yeah.
Okay. Well, thank you again for the excellent talk and for staying up so late over in Switzerland.
Yeah, thank you for having me.
Yeah, and for the audience members, if you have more questions, you can leave them on the app, and I think you will be able to see them and answer them later. And of course, you can always get in touch with them by email. Okay, so our next speaker is Professor Na-Young Kim from the University of Waterloo, who will be talking about semiconductor quantum cavity QED platforms.
Hello, can you hear me?
Yeah.
Great. Hello, everyone.
You're a bit quiet, but you can hear you.
Oh, okay. I hope I can speak up. Hello, everyone. Thank you very much, Paul, for a very kind invitation and introduction. I'm truly excited to present our research progress in the theme of semiconductor quantum cavity QED platforms. Since 2016, I joined the Department of Electrical and Computer Engineering at the University of Waterloo, and I'm also a member of Institute for Quantum Computing. We are at the heart of the Waterloo's Quantum Valley by connecting academia and industries, making strong networks among University of Waterloo, Perimeter Institute, Quantum Valley Idea Labs, and so on. And our unique IP policy really supports our entrepreneurship in quantum disciplines. Now, these are my current and past members of the Quantum Innovation Laboratory working on many different projects. And we like to contribute the community by exploring fundamental properties as well as towards the scalable quantum systems based on semiconductors and solid-state materials by utilizing quantum and nanotechnologies. As a physicist and engineer, I'm truly thankful for appreciating the beauty and the wonder of nature. In particular, from my training, I'm a physicist. I have special lens to look at this amazing lessons that nature teaches us. Throughout the variety of the different type of the materials, conventionally and exotic materials, we decipher the hidden codes and properties inspired by beautiful and rigorous mathematical expressions and physical laws and principles. Upon this solid understandings, we're able to dream how to utilize our lessons and knowledge to make the new devices and systems. This is what we are driving and to do the quantum researches. Along these journeys, I'm very fortunate to have both the internal and external collaborators in Canada, University of Waterloo, obviously, and as well as internationally. In particular, we are fascinated by some solid state materials where many electrons in specific atoms can offer exciting material properties. These are some of the examples I've been studying for the last 2 decades: carbon nanotubes, gallium arsenide, YBCO, and so on. And we usually look at this periodic tables, and these are the specific elements that I've been working on. But this, the examples of the semiconductors, not only with the semiconductors are not possible to make the functional devices, so we have to combine the semiconductor elements with the other elements like kind of the metals and oxides. So by all of them together, we are making the exciting photonic and electronic devices. So particularly, I'm explaining to you about solid-state cavity QED platforms, which we already learned very exciting and aspects from the previous speaker, Yuan. and in this materials. So particularly, I'm going to introduce I'm working on these two the fields like exciton polaritons and Rydberg excitons, and given this time, I'm going to focusing on the first element of the block exciton polaritons, and this project was done with the internal and again the external collaborators. And ultimately, what cavity QED means is to control light and matter interactions in the solid state materials, particularly for us in the semiconductors in the 3,5 gallium arsenide based. And let me first introduce the microcavity exciton polaritons. When you hear about polaritons, usually it refers to a generic term of a photon combined with the matter, the excitation. In our cases is the quantum well. So I'm going to walk you through about the individual components. First, cavity photons. In semiconductors, I'm focusing on the gallium arsenide base. We can make the special mirrors. I call special means like we are utilizing the combination of two different materials to form the distributed Bragg reflectors, can confine the photons inside. But the size of this cavity is so small, so that's why we call the microcavity. And when this microcavity is excited by the electric field, then only particular mode is confined, so that as you see, there's the photon is confined with this the distribution of electric field. We can do this experiment with the reflectance measurement as a function of the wavelength, and you will see that this particular mode is absorbed by the cavity photon, so that you're able to engineer a photonic cavity. So in this case, the optical cavity. For some of you who are more familiar with this, the cavity, it's defined by, the quality is defined by the metric we call the Q, so that so far the gallium arsenide quantum well device that I'm working on has a quality factor is around 3,000 to 10,000, which actually relates to how long we can confine the photon, so that the higher Q definitely helps us to confine the photons to control the light matter interactions. For us, the Q is not as impressively high, and typically the lifetime is about a few picoseconds. One more thing, if I want to emphasize, is that because of the breaking the translation translation symmetry in the growth direction of this cavity, so that we can confine the photon, and effectively this photon can have an effective mass. And for the gallium arsenide based cavity, the effective mass is about 10 to the minus 5 times of electron mass. It's very, very light, but it gains it. And then for quality factor 3,000 gives about the lifetime about 2 to 4 picoseconds. Here are some theorists that we can model this cavity photon in terms of the second harmonic, the harmonic oscillator, and we can represent as the second quantization denotation, so that the Hamiltonian is given by h bar omega c, which is the energy, and then the creation and annihilation operator of c to represent the cavity photon. Next element is the quantum well exciton. So we are again using the semiconductors, the gallium arsenide and aluminum gallium arsenide, to change the band gap engineering. I'm still there.
Yeah, you're good.
Okay. Yeah, it was suddenly there was, okay, so let me just go back to the previous page. So that we can actually make this the two different semiconductors to form the quantum well, then the fundamental excitation of the quantum well is exciton when we shine it, so that we can create the charge carriers of the electrons in whole, and these are the coulomically bound to form the exciton. And for the gallium arsenide case, the binding energy is about 10 milli-electron volts, and then the Bohr radius of this entity is about 10 nanometer. And when, because this is excitation, so it can emit the photon, so that when you characterize the quantum excitons, you're able to see some kind of emission, like kind of shown in this case. Again, it is excitation, so that it carries the mass as well as lifetime. So this is shown here. And you can also express this quantum exciton in the Hamiltonian simple form of the h bar omega and the A and A dagger and A to represent the exciton in a second quantization way. So in this slide, a quick movie to show you how to form the exciton polariton. In other words, there's one entity of cavity photon. At the maximum of the electric field, we place the exciton so that they can reversely energy exchange between two components, and by the dipole coupling in those cases, and we can diagonalize the system in a linear regime. Then we are able to find the two quasi-particle solutions. We call the upper polariton and lower polariton. The signature of strong coupling is seen as anti-crossing of the dispersion. So when you form the exciton polaritons, then this is the experimental spectroscopy of the energy versus the in-plane momentum. Then you see there's an anti-cross behavior to confirm that the exciton polaritons are created. So this is the basic particles for us to study the cavity QD. And because the exciton polariton is the duality, so that we can utilize this particle and wave natures. And the advantages of exciton polariton cases is that we can directly access the polariton dynamics in terms of the energy, momentum wave vector, and spin degree of freedom. And also we can quantify the interaction among this exciton so that we could address some of the exciting the physics as well as the engineering manner. Okay, so in this particular case, it's what we are trying to establish to make the quantum simulators. What it means that we want to simulate some of the quantum system, for example, the electrons in the solid state materials or condensed matter, so that these are the particles and electrons in the matter has the orbital degrees of freedom, as you learned from the basics of physics and chemistry. And the way you can look at it is the electron is in a specific lattices or crystal structures, like the graphene in the honeycomb structures, or the cuprous oxide, copper oxide in the high temperature superconductor to form the square lattice. In condensed matter, how to understand these particles in the lattices by performing either the angle measure of the photon emission spectroscopy to see this energy dispersion relations, or if you perform the scanning tunneling microscopy to observe or measure the electron distribution in real space, so that you could address those correlations and interactions. In our cases, we form the polaritons. We create the artificial lattices, and then we are looking at the leaked photons to characterize the energy dispersion relations as well as the wave functions in the real space. And in order to create the artificial lattices for exciton polaritons, and there are different dimensional engineering the methods, because we have two different entities like photons and the exciton. So particularly 1D, I'm just linking to the previous speakers. Our gallium arsenide is the piezoelectric material, so that we can create also the surface acoustic waves, so which can also as working artificial lattices. But then you can see the variety of different ways to create this artificial lattices. The last 5 minutes, I'm going to show you our latest the results of our work, particularly to form the honeycomb lattices. This method, the way to create this method is utilizing the nanotechnology. And we designed this lattices with the fixed diameter of each side at 2 micron. But then we vary the distance between the site, which we denoted as a D, varying from 3, 4, 5, 7 by utilizing the state-of-the-art nanofabrication technologies. In our case, we also able to change so-called the detuning. Basically, what that means is we can control the amount of the exciton and photon because, as I said, exciton polartons are a combination of these two entities. And once we created them, and using the etching so that you grow the structures all the way up to the quantum well structures, but we stop the grow and then pattern it and then etching it, and then we regrow in this way, so that this method allows us to have a very strong trap potential, about 2 to 5 electron volts, which is about 10 times stronger than the kinetic energy of the kinetic energy of this exciton polariton. So once we create it, then we put it into the cryostat about 4 Kelvin or 4 to 10 Kelvin, and we examine that in the photoluminescence spectra. So let's take to have a very short movie. So let's see. So on the left, what you will see is that energy shot at the particular, the plane of the reciprocal lattice kx and ky on the left, and right y-axis, the x and y axis. By the way, in condensed matter language, on the left is a reciprocal space, on the right is the coordinate space in real coordinates. So the way we can look at it in a more good way is that this is the Brillouin joint of the honeycomb lattices. We cut particular the cross-section of the Brillouin joint. Then what you see is the what we call the band structure energy versus the wave number. And often the condensed matter people show the lowest bands, but in our case, we're able to access not only the lowest bands, but also the higher bands as well. This experimental result is well explained by the theoretical calculation in the single particle pictures, as you see that the very good the agreements between the experiments. And what we can vary as a simulator is that the D, I said the nearest neighbor, the distance, we can vary it. And then we observe it of the same the energy dispersions. And all these things are well described by the single particle theoretical calculation at the bottom. The second quantity we vary is the detuning. In other words, the amount of the exciton versus photons. So from left to the right, we grow the more photon in the left and a more exciton in right cases. You may catch some of the discrepancy when you go more the positive or the more excitonic part. We are able to solve this the puzzle in terms of the two flavor Hamiltonian. Basically, we created the Hamiltonian for the both is the photon aspects of the Hamiltonian section, and then the sorry for this, the photon part and then exciton part, and then this is a dipole coupling, so that we are able to explain what happens in the exciton part. So that the last cases is that from this, what we want to do is we're basically quantifying this, the so-called the hopping integral between the sites. Why is that? It's in the sites and the nearest neighbor and next nearest neighbor. By studying of dispersions, we can quantify that. So this is the last slide. I'd like to end with our perspectives of the exciton polariton quantum simulators in the field of the cavity QD. is we want to address some of the problems like computer science problem of the NP-hard problems we can address, because the exemplariton can also address the spin degrees of freedom, so that they suppose we can build the Ising Hamiltonian or XI Hamiltonian, so that then this would be a revenue to understand some of the practical the problems like traveling salesman problem or the Mexico problems. Another the area we like to study using the quantum simulator is to search the quantum materials, and particularly interested in the topological phases in two-dimensional cases. And there are lots of interesting proposals, and then the works in the condensed matter we try to understand in the context of exemplariton. So this is what we are enjoying to pursue the research. So I'm thanks for your attention. I'm happy to have any questions.
Okay, thank you very much for the excellent talk. You're right on time. So we have 5 minutes for questions. I encourage people to use, so I have the WOVA app here open. Again, I don't see any questions at the moment, but you can pose them through that website app or on your phone or whatever you're using. Anyways, I'll begin. So you showed that really neat movie, going from like a near field to a far field, I think. Well, you said from a real space to a momentum space.
Yes.
Description of your system.
Yes.
I was wondering if you could talk more about like exactly what's happening in that measurement, like what are you varying so you can go between those two pictures?
Yes, so that the thanks Paul for the very technical question, which is very important, right? Because we are all optics, and the real space and reciprocal space are related to the Fourier transformation. So that theoretically you do is that if you have something you know about the real space performing the Fourier transform, then you can access the reciprocal lattice. In optics, we use a lens, and actually this one lens performs a Fourier transformation. So that the way, I'm sorry that I didn't have this set up, but I'll just go to this previous cases, is that by inserting the one, like kind of the number, you're controlling the number of the lenses, you can access either real space and momentum space. So if you have a one lens, then you could convert the real space into reciprocal space or momentum space, and one more lens to go back to that. So okay, that's how we can access. And then we use the spectrometer to do this, the energy result, the data. Yeah, so it's in a sense very easy, like much easier than the condensed matter angle result, the photon emission spectroscopy. So that's actually the beauty of the optics.
And then I feel like I might have missed something important on the honeycomb structure that you showed.
Yes.
So just, yeah, like just in terms of how you're defining this, like, are we trapping electrons in each of these black circles or in between each honeycomb, like in the center?
Okay, thanks for that. I was maybe rushing it. So that this particular cases, we have a longer cavity, so that you could imagine that in the cavity structures, we have a stepped. So the on the old outside is the shorter, and then only the where the circle happens, it's a longer. So that you can imagine the cavity length is large, so that consequently the energy is smaller. So it's inversely proportional to the cavity length to create the in-plane spatial potential for the photons in this case. So basically, variation of the cavity length will give the photonic the potential, not the photonic crystal, because photon crystal is you have punching the hole. So in this case, we variate the distance. So therefore, when you change the detuning, then this potential also varies because it is related to the amount of the photons. So you can imagine when we are the highly red detune or the photon light, we have a stronger potential. because you have to consider this whole field of the photon. But if you go to the exciton state, and the potential is small because physical length will be fixed, but the amount of the photon is smaller, so consequently the potential is smaller. So it's an excellent question. So thanks for asking.
Thanks. Okay. So thank you very much for the excellent talk, and we're more or less on schedule, so we'll move on to the next speaker. But yeah, thank you again. And of course, I sound like a broken record, but you can, in the audience, ask questions on the online app, and the speakers can see them after the talks, and you can start a dialogue there if you have anything you want to ask about. So the third and final speaker of our session is Joe Selfie, who's an assistant professor at the University of British Columbia, and we'll be talking about his nanoelectronics research.
Thanks, Paul. Hopefully everyone can hear me okay.
Yeah, you're good.
Great. Yeah, I forgot to give it a title, and it was because I signed in on the wrong email address to the app. So yeah, apologies for that. So yes, I'm going to talk about the quantum information technologies based on spin and superconducting nano devices today. And yeah, I'd like to thank the organizers for the chance to give this talk. So first thing I want to talk about is spin qubits, which sort of forms the backbone of my research. And spin qubits are qubits made out of that derive their two levels, basically, from the fact that an electron or a fundamental particle has got an intrinsic angular momentum. And there's many different systems in which spin qubits can be made. And so the specific one I'm going to focus on in today's talk, the one that I study, is silicon-based materials. And so the question is sort of, what is special about silicon-based materials? Why would someone study spin qubits in silicon? So one possible answer to this is that silicon can be isotope purified to remove the nuclear bath. So there's a fluctuating spin bath that comes from the fact that there's a nuclear moment, and that causes rapid decoherence of spin degree of freedom of say a nucleus or an electron. And most importantly, that can be entirely eliminated in silicon because there are stable isotopes of silicon which have no nuclear moment. And this is kind of the first sphere, kilogram of silicon that was made out of isotope pure silicon-28 for metrology purposes to define the kilogram. And actually, this has, when you put a few dopants in this, you see that those dopant atoms can have extraordinarily long coherence times for something in a solid. So here I'm focusing on electrons in this slide. Sometimes this is called atoms in a semiconductor vacuum because the material is behaving almost as if it's a vacuum. So this is an experiment on ensembles of dopant atoms in silicon, and showed a coherence time around 10 to 100 milliseconds. And the surprising thing is that when you confine individual electrons in nanostructures, like on the middle and the right-hand side, that largely these long coherence times can be preserved for single electron spins. And what's happening in this device and this device is that you apply voltages onto a set of electrodes that are defined on the surface of the semiconductor, and it allows you either to load a single electron onto, say, for example, a phosphorus donor in this case, or just directly beneath one of the gates, in this case for a quantum dot. And so, around 2014, it was shown that you can get these, substantially long coherence times similar to just an ensemble of electrons bound to dopant atoms, so in these devices. There's been a considerable amount of progress since this first was demonstrated a few years ago. And I'm just showing a cartoon of what those devices look like from a side view. So in this case of donors, you have some Coulomb potential that binds the electron. And in this case of quantum dots, you're just relying on the gates, voltages you apply to the gates. And so this is a sort of the state of the art results that single and 2 qubit gates are now at the errors around 1%, and measurement, well, okay, so actually single qubit gates in measurement can even be below that. And this is, exciting because that's the kind of level of fidelity that you need to start competing with trapped ion and superconducting qubits. And then you can ask yourself, why compete with them? Or what, even better question to ask is, what do you have, what can you do that's unique in this kind of system? So, I mean, one of the reasons why people became interested in this is because silicon, of course, is the material upon which the entire modern microelectronics and classical information technology is based on. And the qubits are the devices are extremely small. I've just shown you that they can make very clean qubits, and these devices are very manufacturable. So small is good if you want to have a lot. Manufacturable is good if you want to make them reliably, and clean is good if you want, good quantum properties. So on the left-hand side, yeah, this is just a picture of a die, and on the right-hand side, this is, an experiment done around 5 or 6 years ago, demonstrating a qubit on a wafer built like this. This is a industrially fabricated device. Okay, so then the next question you could ask, okay, this is great, close to fault tolerant thresholds. What are the challenges with building multi-qubit circuits with this? Well, one of them is clearly the short range interactions. These kind of qubits, as you can see in this picture, the mechanism by which these high fidelities has been achieved is a short range coupling. And that's actually very close, right? 100 to 20 nanometers kind of length scales is very close. And that will make building large scale devices like this challenging. Another one is electric noise. And this comes from, there's a typo here. This should say isotropic, that's correct. The interactions between the spins are isotropic in this 2 qubit subspace, which exposes you to dephasing, this sort of short range interaction. And then you have this issue with crosstalk and density. And then the last one here for electron spin qubits, which is what I've been talking about till now, they have this additional orbital degree of freedom that's a low-lying state. So what my research in the last few years has been looking at is an alternative platform for qubits in silicon and group 4 materials, basically. And it's based on just the properties of, instead of electrons, valence band holes. And so what does that mean? So in the conduction band, the states basically transform like spin 1/2s, and the valence band is a different story because you have atomic orbital angular momentum of 1, and that couples to the spin degree of freedom. So you get spin 3/2 manifold. And the key thing here is that, in this manifold, spin is not a good quantum number. Total angular momentum is. What this gives you as an advantage compared to electrons is a means to simply electrically control the qubits. And what this also gives you, this electrical control, is an ability to build long distance gates via a number of mechanisms. For example, I mean, it was really great. The introductory talk talked about QED, where you can have, a photon in a resonator. Such a thing can work in this case, coupling to the electric field of the photon, or simply just the capacitive interactions between qubits, which you can engineer with gates. So this is a plus. The other plus is that holes don't have this low-lying excited state. But here's the real typical drawback that we wanted to attack, actually, which is these properties sound really great, but not at the expense of coherence, because you need coherence for quantum technologies. And in the past, like sort of 15 years of research, there really didn't seem to be a way around this problem of poor coherence times. We're sort of seeing 100 nanosecond to 1 microsecond coherence times. So this kind of sparked myself and colleagues to start thinking about okay, could we find the equivalent of a clock transition in this system? Like the kind of transition that makes an atomic clock have a long lifetime, where you can manipulate the system, but its Larmor precession frequency is insensitive to fluctuations. And in this case, we would need it to be insensitive to electric fluctuations. And so the whole key behind this story, which first started out as kind of a combination of experiments on whole devices and then theory on the coherence of whole devices, is that the realization that if the spin orbit coupling is big enough, it's not appropriate to treat it perturbatively anymore. And what that non-perturbative treatment allows you to find some situations where you get a level repulsion, and that level repulsion is pretty much always the key to these electric clock transitions. So that was described theoretically in this paper on silicon boron atoms in silicon, which bind holes. Then we performed this experiment, and we showed actually that you could get 10 millisecond coherence time in this system, which is, you know, as long as basically as long as electron spins in silicon. So that kind of turns the conventional wisdom on its head, which said that, you know, if you have spin orbit coupling, when you look at it in perturbation theory, it always destroys coherence. But if you recognize that perturbation theory is invalid and then do the experiment, you get the result that, you know, this long-lived states are possible. And so the vision that comes out of this work, which I've done when I was a DECRA fellow in Sydney, which is where sort of all this spin qubit research came out of, that it can be done for impurities. And now we're working on this to try to show that you can get this control. And the vision is to add scalable to the list of small, clean, and industrial. And on top of that, there's some other opportunities that I'm going to directly talk about. So, you know, instead of what I'm going to show you now is a couple of different results that are kind of have come out of my group. We set up in 2019, January. My DIL fridge was installed sort of March 2020. And I'm going to show you two or three different results that have come out of our work in the group. So the first one is about single hole nano devices. And here what we're looking to do is just get more control over single holes. And we do that by making whole quantum dots instead of impurities. This is, you know, this allows you to get more control over the constituents and build what I think is more exciting quantum technologies. A sketch of the side view of the device looks like this. And there we have a germanium quantum well with germanium silicon barriers on the top and bottom. These interfaces are very clean, which is a really big advantage for this hetero interface kind of devices. You can move the qubits away from a place where there's charge noise, which is near the surface. Then we deposit ohmic contacts and bond pads and gates on top of this in order to be able to inject carriers and control the potential. And what that allows us to do in this picture, which is a top view, is to load a single hole into this space, okay? Into this space where this plunger gate is. That's called a plunger gate. And we build these devices at UBC using materials, the quantum well materials supplied by TU Delft in the group of Giordano Scapuzzi. And we build the ohmics, gate dielectric, and nanoscale top gates all here at UBC. The advantages of this device, which I just want to reiterate, is that there's no value degree of freedom like there is for electrons. We get control over the qubit electrically because of the spin orbit coupling. We have these high quality interfaces, and germanium on silicon actually turns out to be an industrial technology that's done on large scales. And, you know, it's no less industrial than silicon is. So, and the reason to go to germanium is actually because a silicon well won't confine a hole. You need germanium. And germanium, what's exciting about it is it can also be isotope purified. So we don't lose this perspective for long coherence times. Okay, so now I'm just going to show you just a few preliminary results taken out of our dilution fridge last fall on these devices. And I'll talk about superconducting, our work on superconducting devices after that. So this is, again, what the device looks like. And if we apply a bias of voltage from the left side to the right side, the source and the drain, what we can do is cause holes to tunnel one at a time underneath this barrier into the dot, and then to the reservoir, again, underneath this barrier by tunneling. And this is the signature you see of that in a transport experiment. And the signature is simply the famous Coulomb diamonds that you see here, where the current drops below the value that we can measure. From these, we can characterize the basic properties of the devices, like the energy required to load another hole on top of the existing holes, and how much coupling there is, for example, of the gates to the holes, and you know, we get a value that makes a lot of sense, around a few millieV. You know, our plunger couples to the quantum dots at the most strongly, so we know that our hole is right underneath the plunger. And then we see, for example, these barrier gates here allow us to shift the energy of this peak here. There's actually a peak in the current there, and voltage is applied to the barrier, allows us to shift that, and we see that that shift is relatively small compared to the plunger, which again is just telling us the hole is where we want it to be. So this is a very simple device. It's a single hole device, and we're working on scaling this to multiple quantum dots. Another thing that we've looked at in that cool down from last fall was charge noise spectroscopy. So, you know, what eventually these systems are not just used for qubits, but also to do readout of the spin on each qubit by a technique called spin to charge conversion. And in order to do that, we use the fact that the current as a function of voltage has this kind of peaked-like structure. And I'm not going to go into too much detail here, but you know, the charge noise in our devices is kind of at a reasonable level. So our next steps are really to go to multiple quantum dots, and we're looking at the fact that our particles that we can confine in our quantum dots are fermions. That's a key, so that they can actually, you know, each of our orbitals, it's not just spin up or spin down, it can be occupied 0 times or 2 times with a spin up and spin down, and that allows it to directly mimic electrons in materials. And then you can think of each of these plunger gates as a site. Then the next thing that I'm going to briefly go through is our attempts for integration of these devices with superconducting devices. And so why would we do that? Well, typically for superconducting devices, one of the interesting things is there's, as UN told us, there's a lot of development of tools, techniques, QED that goes with typically involving, let's say, microwave superconducting devices. Then there's usually what you need is a nonlinearity, you know, to make the level spectrum anharmonic. And typically what's used for that is aluminum allox Josephson junctions. And you can build all kinds of devices with this. Amplifiers, converters. You can do enhanced sensing, enhanced qubit coupling with these nonlinearities. So the downside of spin qubits, from this perspective, if we want to make use of the superconducting technology, is that spin qubits need magnetic fields typically, at least quantum dot-based spin qubits do. And these magnetic fields destroy the superconductivity, and in particular, these Josephson junctions don't like them at all. So what we've been looking at is kinetic inductance-based superconducting devices. And here what's known now is that you can maintain high quality factors in resonators because of the fact that you can suppress the dissipation that comes from magnetic vortices in superconductors when you apply magnetic fields. But what's not really known, or is rather totally unexplored, is the nonlinearities in those devices in high magnetic fields. And that's what we've looked at. This is a schematic of our device. And this one is a simple like 50 ohm waveguide coupled to a ring. And that ring is a kinetic inductance nanowire. So it's actually made up of microscopically lots of tiny Josephson junctions that are the grains in a material. I'm gonna start speeding up a little bit because I see I don't have a lot of time left. The concept is to build a simple resonator-based parametric amplifier. Then we have a pump and a signal going through this top waveguide, and they interact with each other when they're inside of this cavity. And that allows us to amplify the signal by 4-wave mixing, and 3-wave mixing is also possible. So these are the two 4-wave mixing terms. The key thing here is that this is a nano device. It has a nanoscale cross section, a small thickness, 10 nanometer and 100 nanometer width. This makes the kinetic inductance dominate the magnetic inductance and allows this nonlinearity to be very effective. And we measure this at 8 millikelvin in a Dill fridge. So I'm gonna skip through this slide, which is basically saying what's happening in with our basic device properties. And I'm gonna talk about the nonlinearities. So the first nonlinearity we see here is the self-Kerr coefficient. And as we add photons to the resonator, we're getting a shift in our resonance frequency. Same with this cross-Kerr coefficient. So one, the resonance frequency is shifting because of pumping on another one. And this is the kind of characteristic line shape we expect. It's, behaves exactly as we expect with increasing power. And we've looked at this, self-Kerr and cross-Kerr. And then the key thing is that the thinner wire, the 0.1 micron, has the stronger Kerr coefficient because the critical current is smaller. That's the scale that matters, the critical current. Then we see that when we ramp up the B field, the Kerr coefficients are just increasing ever so slightly. And that's because we're slightly lowering the critical current as we apply the magnetic field in the plane of the superconductor. Then our next step is let's use that as a means to do amplification. And I'm going to skip through this slide and just show you the basic kind of punchline, which is that when we control the relative phase between the signal and the pump, which in a degenerate case are at the same frequency, so we are modulating the signal, we get a phase sensitive gain, and this can be used for noise squeezing and amplification, or parametrically enhancing couplings between qubits. And the punchline of this is that we get this phase sensitive gain versus angle, relative angle, and then we see that that is maintained at a very high magnetic field of 2 Tesla. So this is actually, as far as we know, the world's first parametric amplifier in the microwave regime based on superconducting technologies that operates at a high magnetic field. And this sort of amplification and de-amplification with the 2 pi periodicity is the key there. So I'm going to skip through this slide again, and I saw Paul show up, so I'm going to end off by saying, just by thanking you for your attention and saying, thanking my group for the excellent work. And yeah, I'd like to take any questions you have.
Okay, so thanks a lot, Joe. A couple minutes for questions. I, again, don't see any on the forum, but maybe I can ask a bit more about these kinetic inductance nanowire systems. So if you can go back to the slide that shows the little gap and like the nanostructure.
Right, yeah.
Material.
Yeah.
So are we to understand that there's like a periodicity in these gaps, or is it just that the material itself is granular?
Yeah, so the material, it's an alloyed superconductor, so it's like pretty disordered granular material. And yeah, and the resonator itself has a little gap here, and that's just where, this is just one of the types of resonators you can make. But yeah, the real kind of key, these little boxes with the squares through them are basically like little Josephson junctions, and we've got them distributed throughout our whole system. And the kind of amazing thing is that in spite of the fact that, this is a very granular material, we get, reasonably well-behaved kind of system out of it.
And those Josephson junctions are like effectively created by the granularity. They're not engineered. Like
Exactly. So that you might have heard there's a system called granular aluminum. And in that you have, well, pretty obvious, you have aluminum here, and then the gray part will be allox, like and then that's really like a kind of analogy to a Josephson junction. Then in our case, this is nib-nitride. And their grains, this is a disordered material as well. Okay. This graininess persists here too. Yeah.
Right. We actually have one question in the Q&A. So it's, could you elaborate more on the fermionic simulation? What kind of systems are these devices suitable for simulating?
Yeah, that's a great question. And that's really one of the most interesting things for me about whole spin qubits. But yeah, so, and spin qubits in general. So, I mean, it's really, the idea is that if you want to take from a step back, if you have a material that has spin and charge, that is not very natural for a quantum computer to simulate, because qubits are not fermions in most systems. So in any kind of problem like chemistry, quantum materials, magnetism, the Coop rates, where, you know, whole dope Coop rates for high temperature superconductivity, the charge degree of freedom plays an important role. And so those are the kind of, you know, if you have spin plus charge and the charge number fluctuates on the sites, that's what this kind of simulator is good at. So I just to give like the classic example, you know, whole doped Coop rate, you know, okay, just from the point of view of a doped Hubbard model, right? Like, you know, it's, if you pretend it's a single orbital whole doped Hubbard model, then yeah, you can simulate it with this kind of system.
Cool. Okay. Thanks for the excellent answer for the question. So we're 1 minute over. So we'll wrap up now so you'll have time to go to the next session. I'll just point out that we had over 80 people in this session at one point. So it was really well attended. And thank you to everybody who made the time to come up to the talks. And of course, thank you again to the speakers for their excellent presentations.
Thank you.
Bye.